we have people waiting. Okay, I'm gonna do a short introduction and then I will handle the floor. Okay, so let's start. People will still join us, I suppose. Okay, so hello everyone and welcome to another talk in our webinar series. This webinar is being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA and CTI. Today, we have the pleasure of having Dr. Raffaella Margutti, professor of the Department of Astronomy and Astrophysics at the University of California, Berkeley. Dr. Margutti is an astrophysicist who utilizes observations of transient astrophysical phenomena, including stellar explosions and stellar tidal disruptions by supermassive black holes. Her research focuses specifically on the biggest explosions and disruptions that occur in our universe: supernovae, gamma ray bursts, compact stellar mergers, and tidal disruption events. She investigates the physics of these events by combining broadband observations across the electromagnetic spectrum, including X-ray, UV, optical, infrared, and radio. The primary goal of her research is to understand the nature of the physical processes that regulate such dramatic displays. Raffaella, if I may, thank you very much for having accepted to give us this webinar talk today on such an exciting topic. The floor is yours.
Thank you so much, Rodrigo, and thank you everybody for joining me today for this talk. Yeah, so as Rodrigo was saying, I'm going to give you a little bit of a tour in the world of multi-messenger astrophysics, and I gave you a little bit of a different title, I think, but it's the content is the same. So I would like to discuss with you where is the frontier of the field right now in this world of where we can combine gravitational waves with neutrinos and photons. So just one slide to motivate the study of what I call explosive transients. So why we care about the stars that are ending their lives. So here I put on the slide the most important reasons. So some of them are really good in telling us distances in our universe. Those are our type 1a supernovae. For the more massive stars, those are the place where some of the heaviest elements in the universe are produced. So when they explode, they release to the environment their heavy elements. And while doing so, they also release kinetic energy, which is the driving force behind those outflows, so the purple thing that you can see in the upper right corner. Of course, exploding stars are also the way that our universe has to produce the most compact, the most extreme objects like black holes and neutron stars. And by now we know very well that we are now in the position to detect these objects when they merge, when they produce gravitational waves. So we have these laboratories of extreme physics that for free in our universe, and that's what makes me particularly excited about this transient. So let's try to understand what are the big open questions in the field. Here you can clearly see that we have two big question marks. So we do know that there are massive stars in the universe, and we can describe very well their explosions, but we do not know yet what stars explode like which supernova. So hence the first question mark. Likewise, even after the supernova happens, we really have hard times understanding what is left behind. Is that a black hole? Is that a neutron star? We basically don't know. We do know for a fact, though, the massive stars, most of them hang out in binaries, and some of them are able to stick together until the end, and they merge, producing gravitational waves that we can detect right now, and also light. A big question in the field is, even in this case, what is left behind? What is the nature of the compact object there, which is another way of asking the question, what is the equation of state of nuclear matter? So if I were to spell out the open questions, here they are. What are the stellar progenitors of these supernovae? What happens during the times while they approach their death, their collapse? what powers their explosions? What are the properties of these newly born black holes and neutron stars? What are their masses? What are their spins? And when they manage to stay together and they merge, how do this merger look in the electromagnetic spectrum? So those are fairly big questions and fairly basic questions. So why now is a good time to try to attack and address these questions? And here I'm going to give you an answer in 2 points. The first point is very much related to a technological revolution. So this is a moment in human history where we do have the capabilities to take pictures of the night sky and every night go back to the same patch of the sky and ask ourselves, is there anything new? Here, I'm emphasizing a few of the surveys. I'm emphasizing the Young Supernova Experiment, EASY, that is run on Pansters. I'm one of the 5 co-founders of this survey. But of course, I can't avoid emphasizing ZTF as one of the major players in the field, and looking forward to LSST, and maybe a couple of years, LSST is going to play a major role in this world. This type of revolution is not only happening at optical wavelengths, but is also happening at radio wavelengths. And here I am pointing at SKA, for example. And the hope is, at least my personal hope, is to have the high energy sky in the soft X-rays, especially, to be able to catch up with a wide field instrument. That is not clear that will be the case. So a new addition to this realm of surveys is LS4, is the LIneA Southern Survey, and that is headquartered here at Berkeley. The PI is Peter Nugent, LBNL. And I want to emphasize this survey, first of all, because I've been deeply involved with it, but also because as you can see in the red box in the lower right corner, most of our data will be public immediately. So the goal here is to have a smaller telescope that has a wide field of view. And you can think about this as, if you're familiar with ZTF, as a half of a ZTF survey in the south to complement LSST. And we will be using the same filters. So the comparison with LSST is going to be easy. We can basically complement LSST both in cadence and in depth. In depth meaning when LSST saturates, LS4 will not be saturating. So we will have that information too. So the idea here is effectively to use LS4 to fill up the gaps of when LSST can't observe. Why can't? Because there are so many scientific cases that are driving the cadence of LSST that not everybody can be happy with one choice. Oh yeah, and that's I always find funny, that's a donkey in the picture. So if you're interested to know more about LS4, just let me know. There are many opportunities that I think will be interesting in the future with LS4 data. We're supposed to be on the sky in December 2022, so at the end of this year, modulo all the COVID things, as you might have guessed. So we have been having these new toys, these new telescope surveys for a while. So what have we been doing with this? So as every single time we start, we have something new. That means that we are able to sample portion of the parameter spaces of things that we already knew, like supernovae, for example, that were not accessible before. And here, I'm putting a plot of luminosity versus time for a supernova. And the message here is that until 10 years ago, the supernova field was heavily relying on amateur astronomers to discover our supernovae. And amateurs are fantastic human beings, but we tend to find things when they're bright, which means that on average, we were missing out on the very early phases of supernovae. And when I was a grad student, I was taught that stars just wait quietly in the last years before core collapse and nothing happens. But instead, right now, we know for a fact that this is not true. This makes a lot of sense to me from a scientific perspective. Stars actually do know that the end is coming, and they do experience a number of eruptions. Most of them do, for reasons that we do not understand. So not only we could explore new pieces of parameter space of things we already knew, but as every single time that we had new capabilities, happened, we were able to find new types of transients that we were actually not even aware of. So here I am selecting two types of transients, two newcomers. Those are the superluminous supernovae that you see in blue in that cartoon, that are the most luminous optical supernovae, and very fast transients, which are in the cartoon in red. The reason, I'm going to try to give you an intuition of why we did not know of this transients until 10 years ago for superluminous supernovae and 5 years ago for these fast transients. And the reason is the following, that first of all, it has to do with the time scales of our observations. We were used to do some sort of monitoring similar to the vertical dashed lines. You can clearly understand why fast transients were totally missed. They just fall in the gaps. And for superluminous supernovae, the reason why they were missed is that sometimes the delta brightness was not large enough to actually trigger, to actually send out across the background, and or we were actually looking for type 1a supernovae that have a rise time of a couple of weeks. Superluminous supernovae have typical rise times of 50 days or more. So we were just not finding them because our algorithms were not tuned to find this transient. So a huge lesson learned for the future. We only find what we're looking for. So we went from this type of monitoring, dashed lines, to this type of monitoring, so over multiple seasons, and also much faster, that allowed us actually to recover these new types of transients. The other reason why we were not aware of this type of transients is about where we were looking for these transients. So as I said, until 10 years ago, we were relying heavily on amateur astronomers that tend to like the previous galaxies in the sky. So that meant that galaxies like the one in the lower left corner were really popular among amateur astronomers, but galaxies like the other one, that little smudge that you have in the other picture, not so much. And it just turns out that these transients, fast transients, and superluminous supernovae do show a preference for little dwarf galaxies that we were just not targeting. So how we were looking for these transients and where we were looking for these transients is the reason why we did not know of them until now. The second point I want to give you of why now is a good time to actually get involved with time domain astrophysics has to do with multi-wavelength astrophysics, so we can play this game across the spectrum. And in my mind, this is just the first step towards what is now reality, which is multi-messenger astrophysics. So a combination of photons with neutrinos, and of course, the latest comers, the gravitational waves. So point number one, these surveys are giving us discovery power, are telling us where to point our telescopes in the sky. And point number two, the multi-wavelength studies are giving us the possibility to understand what's going on, to actually map the physics of these transients. And combining discovery power and understanding is a great way to make progress in a field. And that's why time domain astrophysics, now called multi-messenger astrophysics, is flourishing right now. So going back to the big questions that we had. So how do we try within my team to answer to this question? So when I give you a feeling of how we function on a day-to-day life. So here's how it works. Our motto is no photon is left behind. So anytime there is something that we flag as very interesting in the sky, we trigger all the programs that we have approved on a variety of facilities, and we do studies across the spectrum. So we have programs all the way from the gamma rays all the way to the radio. And here I am using as an example one of my favorite transients, 2018 COW. So as you might guess, all of these facilities are not sitting there idle waiting for us to tell them what to do. That means we are effectively interrupting other astronomers that are trying to do their job. And so this entire business of time domain astrophysics also brings in some sociological aspect that is also, I also find particularly interesting, how not to create too many enemies in your field before you get tenure. That's how I say it. Okay, so how do we work? I built within my team an end-to-end experiment. So we have a discovery engine, which until let's say 10 years ago, a discovery engine would just consist of a telescope survey. That would be totally enough. Right now, it's definitely not the case anymore. And this discovery engine is actually made of two parts. One is a telescope survey, here again emphasizing easy and CTF, but you also need something that is all computing based, what I refer to as AI. So it's machine learning. We use a lot of machine learning algorithms to actually filter out the things that are either not astrophysical, those are actually now they're the easiest things to filter out, all the way to try to classify at very early times our transient, try to get an idea of what these are. And only after a trigger, so a variation in the sky gets above our threshold of interest, it gets passed to the follow-up team that starts triggering all of those facilities that you've seen in the other slide. So that's how we work. So let's move forward and let me focus with you on the first half of the question, which is what happens to the stars when they're approaching their end. And we have, from an observational perspective, we have three ways we can try to answer to that question. And theoretically, this is a place where a lot of uncertainty is. So it is a place where theory can actually be guided by observations. So what can we do there? So we have three main ways. The first is use direct observations of that location in the sky. And the concept is extremely easy. We detect a supernova, and then we have all the images that we have taken in the previous nights, and we just go back and we ask ourselves, was that star doing something special that maybe did not pass our threshold to trigger our interest before, but it was a star doing something. And that's how the Supernova 2009 IP, which is a landmark event in astronomy that really woke up the community, I would say, was found. So as you can see, so Supernova 2009 IP, first of all, the name could not be more misleading. It was not a supernova in 2009, but the star experienced a number of outbursts that were large enough to actually lead us astronomers to think that it was a supernova. So the star experienced a number of outbursts, and only in 2012 exploded. And the important thing here is that 09 IP is not alone in this with this phenomenology of having outbursts before stellar death, as close to the end as you can see 40 days before. So we are actually witnessing now a number of stars that before core collapse do go through this series of outbursts. So 9 IP was the event that really sent a huge, powerful message to the community that, hey, we are missing something in our understanding of massive stars. Why do they go through outbursts where they eject a sizable fraction of a solar mass? But at the same time, there was something that made some of us believe that maybe this sort of effects were not important for all the stars. And here's what I mean. So 09 IP was a particularly lucky case for which HST in 1999 actually got a picture just by chance, because HST was trying to observe something else. So this is a very lucky case where we can actually look at an image taken years before explosion and pinpoint the star that is now exploding. And if you do numbers, the brightness in HST images is such that you conclude that this star is an extremely massive star. And this was good and bad, because it was good, great, we could actually understand the type of star that we were dealing with. But it was bad because it led to many of us to believe that maybe this phenomenology of eruptions maybe is just something that happens in the heaviest tail of stars. So at the end, this is way less than 1% of the stars. So why should we care? And what I would like to convince you today is that this is actually not true. And all stars that explode across the entire spectrum have been witnessed to experience eruptions before death. So there is something that we are missing in our understanding of massive stars that leads to these eruptions. So we'd better understand it. And here I'm using supernova type 2P supernova 2020 TLF, and type 2P supernovae are the most common type of supernovae, to bring home the point that if we go deep enough and we study these supernovae before they explode, which is what you see in that second panel on the left column, we can clearly see that before explosion, which is time 0 on that plot, you can clearly see that the star was not quiet. So in the hundreds of days before core collapse, this star felt that the end was coming and experienced a very long rebrightening. So these are the most common type of explosions. So this is telling us that the most common progenitors also share this phenomenology of experiencing outbursts. So this particular event is the first sign that we detect directly this type of eruptions. However, I need to acknowledge the fact that it has long been thought that the very powerful UV emission that some of these supernovae have at early times was actually powered by a shock slamming into material. And that was a fantastic prediction from the theorists to tell us that there should be some eruption before. But here we are, we can see it with our eyes that yes, that is true. The stars can actually have outbursts. So now it comes the question, so if they are so common, why it is so that for the most common supernovae, we've been missing them until very recently. So here is the question, the answer. So you have absolute mag on the y-axis and time on the x-axis. And here my student Wien Jacobson-Galin has plotted up a number of supernovae that experienced outbursts before. And you can clearly see that the type 2 Ps, like 2020 TLF, their outbursts are significantly fainter than for other types of stars. So the key message here is that even for surveys like CTF or EASY, the same outburst placed at 100 megaparsecs will be completely entirely missed. It's just because these eruptions are faint. But I also want to emphasize, if you look at the bottom dash line for LSST, this is a place where instead LSST will really shine. So this is a place where LSST has a depth and has the cadence. The cadence of the wide deep fast survey is totally fine, and it has all the capabilities to reveal all these pre-supernova lives of this supernovae. So yeah, the gap between the most powerful outbursts that we've seen and the faintest one is several mags. And that's what I was saying, that we really need a deep survey, and LSST will be that one for us. So here I'll try to populate with you this diagram. This is how I think about my field of explosive transients. Is a parameter space of luminosities and time scales. And I keep asking myself, where is the place of this parameter space that might be becoming interesting in the next years? And the first place where I think there will be a lot of discoveries has to do with the pre-supernova outbursts that I just emphasized. And this is very much linked to the well, not so much the future existence of LSST. So this is a place where I do expect we will have a lot of surprises. So it's a good place in my mind for students to get involved. So let's go now to the second way we have to actually learn about this life of massive stars before the end, which is what is now known in the field as flash spectroscopy, a tool that was developed by Avishai Galliam and team mostly. And here the concept is also very, very easy. So we have a stellar explosion. This stellar explosion will, the light will ionize matter just that is very close to the explosion. And the idea is that this mass was left behind by the progenitor just before death. So we are using the first photons from the supernovae to illuminate the leftover from the star just before explosion to understand the chemical composition of the outer layers of the star before explosion. So here I'm again emphasizing a result from my team. So let's focus on the H alpha line profile that you have in the upper right corner. So first of all, you can see that this profile of H-alpha varies very quickly. Those are 3 spectra that have been obtained over 24 hours. So for all of you that are spectroscopists, you understand right away that is a challenge to get 3 spectra in the same 24 hours. And also not only need to be quick once you know where to repoint, but we also need to be extremely good in identifying these targets when they are extremely young. So as you can see, we were able to get on target within 1 day after explosion. So it's technically challenging, but the rewards are huge. And in this particular case, this is a calcium-rich transient. That is a transient that people associated with white dwarfs. White dwarfs explosions. In this case, we were actually able to find signatures of hydrogen in the outer layers of the star, which had implications about the nature of the progenitor, as you might have guessed. So this 19HK transient not only was detected in flash spectroscopy, but also showed the first X-ray detection of a calcium-rich transient, which leads me to the third way we have to learn about the lives of massive stars before death, which is shock interaction. So the idea here is the following, that we have our star, it explodes, and this launches a shock in the environment that is a well-known way to accelerate particles. Particles later cool down through radiation, and they are very, very well-known sources of X-rays and radio through synchrotron emission and branch Raman emission. So here the idea is that if our star was not well behaved and produced a number of eruptions, so we have in our environment a number of shells, those spikes that you can see in the cartoon, the idea is that the shock that propagates into this environment would retain memory, while the radiation dissipation of the kinetic energy of the shock through radiation would keep memory of this very disturbed environment. And since the shock is much, much faster than the velocity of ejection of this material before stellar death, that means that the shock can actually act as a very powerful time machine and bring us back into the past of a star. Here's what I mean. So if we do careful monitoring of the supernovae in the X-rays and in the radio, and suppose we do this monitoring for 1 year, well, after 1 year, the shock has caught up with material that was ejected on average a factor 100 to 1,000 times before. So we are catching up with material that was ejected 100 years to 1,000 years before explosion. So by mapping this shock interaction with time, we can actually reconstruct the density profiles of the stars. And this is just a slide for the radio astronomers among the crowd. So this is how the radio evolution of a supernova looks like. It goes from the gray line. You're looking at a SED evolution with time. It goes from the gray line all the way to the light blue line. This is synchrotron. Is a synchrotron self-absorbed spectrum that then later allows us to actually compute parameters of the environment, like the density that is in the environment, and that we use later to map to stellar progenitors. So of course, after we embarked in these studies of X-ray and radio of supernovae, and the first time you do it in a, let's say, as homogeneous way as possible, you always end up encountering some really, really special events. And here I'm emphasizing a supernova 2014C. You're looking at a Nusser image. So these are hard X-rays from an extragalactic supernova. And this image is particularly special to me. That's what you're looking at is effectively the first hard X-ray image of an extragalactic core collapse supernovae that we were able to follow from explosion all the way until now. I have to say that many years after 2014C exploded, this is still a source that is detectable. So the reason why 2014C is so special is because it underwent a very remarkable metamorphosis. So, and let me explain you what happened for this supernovae. So let's focus first on the lowest panel. This is a cutout of the spectrum around the H alpha line. And if at very early times, this supernova just looked like the most common hydrogen stripped supernovae core collapse I've ever seen. Nothing remarkable. But then we waited a few hundreds of days, and as you can see, the H alpha profile starts to build up, and that is extremely uncommon around hydrogen strip supernovae. And I have to say, at the time of 2014C was one of the few events that was witnessed doing that. And not only this is happening for the H alpha line, but if we now plot what happens in the radio with stars, blue stars, and in the X-rays with red stars, we can clearly see that both the radio and the X-ray luminosity increases with time. And again, this is extremely unusual for supernovae to have increasing radio and X-ray luminosity with time on those time scales. So what's going on here? So in this case, the interpretation is the following. And I'm sure you already have understood the game here. So we were expecting our shock to probe a medium that is hydrogen-free and with just decaying density. But instead, what we were seeing was that this shock at some point smashed against a wall of hydrogen-rich material. And that's the reason why we see the H alpha line growing so fast. But also, the wall of material allowed the shock to have a higher than average efficiency of converting kinetic energy into radiation, and hence we see this enhanced radio and X-ray emission. By modeling all of these photons, so putting together everything we had from the radio all the way to the X-rays, we were able actually to compute parameters of the environment of this supernovae. And we were able to understand that, first of all, this hydrogen-rich shell was close by, was very close to a progenitor that was otherwise hydrogen stripped. And second of all, this shell contained of the order of a fraction of a solar mass of material. So it was not tiny, it's a kind of a large fraction of material. So the most important question is why we do have a shell of hydrogen-rich material sitting so close to a star that exploded as hydrogen poor star. And this is something that is extremely unusual if you try to interpret this event in the context of single star stellar evolution, that the theories that we had before 2014. So there are two potential ways to explain why that hydrogen envelope was ejected. And one has to do with nuclear burning instabilities that are related to the star that is dying. So here the idea is that for some reason, during the last stages of nuclear burning, we deposit some energy at the base of the envelope that is hydrogen rich, and we explode the envelope right before a core collapse. In this case, the mechanism of envelope ejection knows that the end is coming by definition, because it's tied to the nuclear burning timescales of the basically nuclear burning cycle of a star. So if this is the correct answer for 14C, we would expect to find these hydrogen-rich shells almost always around massive stars of a certain mass. A completely different explanation for 14C is that no, this has nothing to do with the primary star, but the envelope ejection is instead a consequence of binary interaction. So it's my companion. And in this case, the companion to level 0th level does not know that the end is coming for the primary star. So if the explanation number 2 is the correct one, then we would expect a very, very broad distribution of shells positions in the environment of massive stars. And as you might have guessed, based on n equal 1 event, 14C, back then we could not answer to this question, which of the two mechanisms is correct. And the only way to answer to this question is actually by putting together a sample. So we need to use statistics to answer to this question. So what you have here is a fairly dense plot, but the key message that I want you to bring home is the following: that the shaded regions in the plot emphasize our level of ignorance when it comes to answer to the question, is there a shell in that supernova explosion at that time after the explosion? Is there any evidence of it? And we tried to answer that question with the most complete data set we had, which is in the radio. And as you can see, the shaded regions are quite large, and they are embarrassingly large after 1 year, I would say. So the key message here is that right now, all we can say is that we do have evidence for at least 10% of the stars to actually have these shells at the location of 14C. However, right now, the field, based on what we know right now, it's still all consistent with all stars actually to experience envelope ejections before stellar death over a variety of timescales. So let me summarize here what are the 3 ways we have right now to actually try to answer to our question about mass loss and massive stars. So we have these 3 ways, which is flash spectroscopy, that is telling us what is the material made of. We have direct imaging that is mapping these eruptions directly. And these 2 tools tells us about the environment that is very close to the star that is exploding. Why? Because flash spectroscopy, because this is how far the burst of radiation can ionize stuff. And for direct imaging is you're seeing the time scales over which we had active time domain surveys. So it's like 10 years or so. And the only way that we have right now to go observationally, to go from T0 to T minus 1,000 years is actually to use the supernova shock as a probe of the environment and try to reconstruct the lives of the stars. So where are we going from here? So the first goal, the first thing that we're doing within my team is to try to shrink those shaded regions to something that is way more manageable and something that can be used to answer quantitatively to the question, is this my companion that is messing up with me, or is the primary star? So a systematic radio to X-ray monitoring at early plus late phases of transients. And as I said, there is that dividing line at 1 year between good and bad. That's nothing to do with science, but is reflecting effectively the life cycle of proposals on our radio facilities, which is quite funny, I think. So, and then the other thing that we can do is to actually try to explore a new parameter space that is almost entirely unexplored in the world of radio supernovae, which is what happens many years after explosion. And this is where VLAS, the VLA Sky Survey, comes into play. So the way, as I said, the way we try to understand if we want to trigger or not on a particular transient every day is by collecting all the information that we have at that location in the sky. And so that means that we put together information from all the surveys that we had so far in the core, that part of the sky. And among those, there is a very recent addition, which is VLAS, the VLA Sky Survey. So we started realizing that many supernovae actually had very bright radio sources many years after their explosion. So here I'm using O4DK. You can clearly see the very, very prominent radio source in VLAS, and that is an image taken in 2019. So not only, and that was not really not limited to O4DK only. So there are many more supernovae that showed an incredibly bright but also luminous radio emission years after explosion. And this is a complete new territory that makes us extremely excited. So what I'm trying to put things into context with this slide, you have a luminosity on the y-axis versus time scale, and you have in blue the hydrogen strip supernovae from the literature to give you a feeling of where radio supernovae would fall in this parameter space. And then you can see the VLAS supernovae, the orange dots, and the relativistic supernovae, which are also VLAS targets in this case, that are with the green squares. And the take-home point is that these VLAS observations are really covering a new portion of the parameter space. First. Second of all, you can clearly see that the typical trend of normal supernovae would be of a decaying radioluminosity with time, and that these VLAS supernovae are much brighter than that. So this is to say that there is something, most likely something more interesting than we thought about the late time radio emission, late time radio life of a massive star. And we also started a deep survey with BLA, a deep snapshot survey with BLA, PI'd by Michael Stroh, that will be able to actually go much deeper than VLAS and survey the entire luminosity function of radio supernovae at later times. So stay tuned. So why we got so excited about this VLAS radio supernovae? Let me try to give you one slide, one answer to that question. So first of all, the world of supernovae and the world of supernova remnants are pretty much detached. This is also true from a sociological perspective in our field of astronomy. But there is a knowledge gap between all we know about very young supernovae, let's say a few years old, and then what we know about the youngest supernova remnants in our galaxy, let's say a few hundred years. Yet, inside this knowledge gap, there might be very, very interesting things happening. So the first thing that might happen that might lead to a radio rebrightening is if those shells that we were talking about for 14C, if those shells are not as close by as in the case of 14C, but they are much farther away in the environment, so that the shock takes a while before it impacts the supernova, the shell, but it does lead to a late time rebrightening. This is interesting because it would allow us to actually add data points to our understanding of when those envelope ejections happen in the life of a massive star, and definitely points at some unusual evolutionary path of that star. The second reason, the second way we can have radio rebrightenings at late times is if we have a relativistic jet that, like think about that as a gamma ray burst like supernova that was not pointing at us originally when it was launched, but with time the jet decelerates in the environment, and that leads to a less and less severe relativistic beaming. So the cone of radiation opens up, and then at late times, at some point, we see the emergence of this radiation finally. So this would be extremely exciting because we have failed so far to find these off-axis jets from massive stars. We do know for a fact that they should exist. So gamma ray bursts, we detect long gamma ray bursts, we detect them when they are on axis. So probabilistically speaking, we are missing many of them. So these off-axis jets must be there, but we have yet to find a solid case. And then third, last but not least, is one of the scenarios that are, in my opinion, maybe one of the most exciting, which is that maybe that the radio rebrightenings that we're seeing with VLAS are related to the emergence of a pulsar wind nebula. So that would be a way to actually study the transition between the two supernova remnant, but also a way to learn about properties of the object that was formed. And that's why I think that filling up this gap in our understanding and knowledge between supernova and supernova remnants is actually critical. So I'm keeping an eye on the time. And yes, we do have candidates in all the categories. I have to tell you that in most cases, data that we are collecting right now are consistent mostly consistent with the idea of shock interaction. So for most of our late time radio supernovae, that is, they are powered by shock interaction with the environment. So I'm keeping an eye on time because I have not too long, but I want to give you some ideas of what we have been doing with the other end of the question, which is about what is left behind. So the dream of the dreams here would be to be able to go from this is a star, this is how it will explode, and this is what it will be left behind. A neutron star with this spin, with this mass, a black hole with this spin, with this mass. We're very far away from being able to do that. So we do know, observationally, we do know that neutron stars are formed by stellar explosions. And we take a picture of a famous neutron star in our galaxy from at the center of the Crab Nebula, and we can see our neutron star producing that beautiful display. So we do know that this is a way the universe has to produce at least neutron stars. For black holes, is a little bit more contrived in the sense that we do not have direct proof of black hole formation yet. But the problem is that at early times, even if we do form something, some compact object deep down the ejecta, it's basically impossible for any sort of radiation to leak out because the ejecta is so thick that it would just absorb it. So all we have, our only option is to wait until the ejecta dilutes and some of the photons can escape. And for the Crab Nebula, that meant waiting until basically until now. But now we can have a very good view of the neutron star. But things might actually be a little bit easier if instead of having a very heavy spherical ejecta like the black donut that you have on this slide, what if we start off with way less ejecta? So typically in a supernova, you have a few solar masses of ejecta. How about we start off with a tiny amount, like a fraction of a solar mass? And even better so, if this ejecta is not symmetrically distributed in a spherical way, but is very asymmetric, so that we do have paths that our photons actually can use, paths of least resistance where our photons can leak out much earlier than, let's say, 1,000 years. And this scenario is very much related to a completely new type of transient that are those fast transients that I talked to you about at the beginning of the talk, that populate the orange bar in this discovery phase space. So these are called fast blue optical transients. Some other papers, you will see them called fast evolving optical transients or just spells. So the bottom line is that the field is so young that we don't even agree on how to call these things. But let me give you an idea of what these are and why they are so potentially exciting. So first of all, if we place these transients in a luminosity versus time scale plot, here they are with red stars, and this is a stripe of type 1a supernovae in black, a superluminous supernovae, they are there in brown, and the rest things in the plot are the core collapse supernovae. So we do realize that they populate the very short rise time scales in this plot. They span a huge range of luminosities, which all the way to meet, to compete with the superluminous supernovae, actually. And to me, that means that most likely we're not dealing with one single population of events from a physics perspective. And as every single time in astrophysics that we do not know what we are dealing with, we try to study the environment. So we try to study the difference to infer about the intrinsic properties of these transients. And what I can say is that all the F-bots so far have been associated with star-forming galaxies that tend to be dwarf galaxies. So there is no need to invoke an old stellar population to explain this transients. So why they are so exciting? Because the fast time scales and very large luminosities that these transients can reach tell us right away that powering these transients in the traditional way, which is through nickel-56 decay, is not going to work. The reason is the following: that the luminosity that they reach is so large. They are so large that to power this luminosity, I need a lot of nickel-56 mass. And the mass I need is so large that it would violate the rise time, meaning that the photons would not have enough time to leak out through diffusion through that ejecta over the time scale of the rise. Basically, I have way too much ejecta for these photons to be able to leak out on the time scale of a few days. So great, nickel-56, which is the powering source behind normal supernovae, is ruled out. So we need to get creative. So we need to add another energy term into the equation. And at this point, we are facing two options. One option is I add that extra energy term deep down in the ejecta. This is what you have on your left. Or let me do something completely different. I added an extra energy term outside the ejecta. So in the first case, In the first case, for the very same diffusion timescale reasoning as before, if I can add that extra energy term, fine, but still I can't afford a large ejecta mass, because again, I would violate the diffusion timescales. So if the extra energy source is sitting deep down in the ejecta, that's fine, but the ejecta mass still needs to be small. So a fraction of a solar mass versus typically solar masses. Then with the other option is no need for an extra energy term deep down, centrally located, but let me try to power this transient with just interaction, like a shock interaction with the environment. And in this case, what we would expect is, first of all, that things would only cool down with time. After the shock crash against something, all that can happen, the shock has released the energy, all that can happen is cooling down. We also would expect no fast variability timescales in our transients. Why? Because the emitting surface is large, so we would be washing out all variability timescales below R over T. R over C. And then we also would not expect to see anything moving very, very fast, because our ejecta would have to be decelerated by the shell in the environment. Those were two very popular scenarios that could live happily in the literature for a while, mostly because these F-bots were not found outside the optical band for a few years. And things entirely changed with the discovery of this transient by the Atlas survey, is astronomical transient 2018 COW. And let me go fast forward here just to give you an idea of why this transient is so interesting. So it's an F-bot with very large luminosities, but the most interesting part of this F-bot is what this F-bot did in the X-rays. So first of all, we were able to find X-rays and radio emission from this transient. So we were able to enlarge our vision of what F-bots do across the spectrum. And what you can see here is an X-ray light curve, and just focus on the black dots. You can see that they go up and down, and they do so very fast. This is not consistent with the idea of a very large surface that is interacting with something else. It is actually more consistent with a centrally located source that is varying intrinsically over those timescales. But in the interest of time, let me go fast forward on the hard X-ray properties of this transient. And to fully appreciate how beautiful 18 Cow is, I'm gonna take a step back and remind ourselves of spectra that are very common around AGNs or X-ray binaries. So anytime we have a source of hard X-ray, a hard, let's say hard emission that is interacting with, in this case, some sort of disk, what happens is that the photons can actually get Comptonized. So we do produce typically this Compton hump spectra, and here I'm plotting things between a few kV all the way to 50 kV. And what you can clearly see is that we have that photons at very high energies, they actually lose their energy through inverse Compton scatterings, and then they are absorbed on the low end through photoelectric absorption. And then we do have a beautiful line, that line at 6 kV, which is an iron line. So the bottom line is that every time we have a source of hard X-ray photons that is trying to shine through something, the interaction between these hard X-ray photons and the material lead to very common Compton humps. Now let's have a look at what we found for the cow. And here it is. So first of all, and we look at the spectrum, and we realized that to put together this picture, we needed data from 3 different spacecraft, XRT, and then NuSTAR, and then Integral taken at the same time, which has its own challenges. And then we look at the spectrum, and we realize that, yes, we do have a power low spectrum and low frequencies, and which is very, very, very common among transients. It is our synchrotron, usually modeled with synchrotron emission. But the surprise is what this transient did at very high energies. We do have that hump there that is very reminiscent of what we are used to observe around AGNs, some AGNs and X-ray binaries. And we even have another little bump at lower energies that is also associated with most likely with iron emission. So long story short, we believe that for the cow, we could actually witness a source of hard X-ray emission interacting with the environment, while the environment in our case is provided by the explosion ejecta. So our conclusion is that F-bots are powered by a centrally located source. And I was very excited when I saw a report of a QPO by the NICER collaboration and a paper led by DJ Pasha, where they report the presence of QPO at very early times right after the cow exploded. It made me very excited because, to my knowledge, QPOs are only associated with compact objects with these frequencies in the X-rays. So that means that the implication, the very exciting implication is that for 18 cow, most likely we were witnessing the very first life of a newly formed black hole or neutron star. So I realize I'm at the end of time. So let me just tell you, where are we going from here? So I used the cow to emphasize this new field that is emerging, but the cow is definitely not alone. We have been getting better in finding F-bots and fast variant transients. And a huge shout out goes to the ZTF collaboration with Anna Ho and Dan Perley and Johan Kao for finding more and more of these transients. But the key point I want to conclude my talk with is that I think all of us are very familiar with gamma ray bursts. These are the blue, in this case, are the blue dots in this plot, and they are very powerful sources both in the X-rays and in the radio, and the most luminous in the world of transients. And the one thing I would like you to bring home today from this talk is that F-bots can actually reach the same type of luminosities as gamma ray bursts. They can also launch relativistic outflows. I didn't have the time to go into details, but for CSS 161010 and another event, actually, we were able to find outflows all the way to 0.6 C. So they can definitely launch outflows. But there is one huge piece of difference between gamma ray bursts, which is that whatever is behind F-bots is hydrogen rich. So if you don't remember anything else from this talk, just remember this thing, that we do have another type of, we were able to find a new type of transient that is able to launch relativistic outflows in the universe. And I would probably end here. And unfortunately, I did not have time to tell you anything about what is going on with the neutron star merger 170817, but if anybody is interested, I can also cover that in the question time. Thank you very much for now.
Thank you, Raffaella, for the very, very interesting talk. We have a little time for questions now. If you joined us on YouTube, you can put your questions in the comment section. And if you joined us here on Zoom, please raise your hand and ask your question. So questions? Well, I will start from a non-expert perspective. And when you were talking about the supernova bursts that happened before the big burst, what are the typical time scales? Do we know it? And how will it be enough LSST with I think one exposure each 4 days to detect them?
Yeah, no, that's a great question. So I guess you're referring to, so let me actually go back here, because that's important. So your question is a extremely important one. So what are the time scales? And we do not have a great answer to that question, but the important piece of information are that there seems to be time scales that are repeating among different events, and particularly that 40 days time scale is the same that we find in multiple events, but also in the outbursts. There seems to be some time scale that is not periodic, not at all, but it's sort of a important time scale for the process. You can see that these outbursts sometimes happen very, very close to the time of collapse. So it's just 40 days before, but some other times these outbursts are years before core collapse. And if we look at this other example for type 2 supernovae, this has a very long time scale of 100 days. So this 40 days, 100 days, those are all good time scales for LSST, because in the R band, the cadence is going to be for the wide deep fast of the order of 15 days. So we do have all the capabilities to monitor these things through the LSST. So I do expect LSST to have a huge impact in this pre-supernova world.
Thanks. More questions? Well, I have a lot of questions actually. If I will keep asking if no one has other questions. My second question is, how long can we follow up the X-ray, the effect that we can observe in the X-rays, like 1 year, 10 years?
Yeah. Yeah, another great question. So it depends what supernovae you're talking about. So the normal supernovae are really hard to observe with the X-rays with the current facilities. So your vanilla supernova, if you get one data point or two and you have a detection, I mean, that's already a lot. So for the brightest ones in the family, so gamma burst, easy. Gamma burst on axis, easy. They can be years, no problem. For these F-bots, it took around I think, so our last detection was 6 months afterwards. So F-bots can actually be very, very easy to detect in the X-rays. Their problem is that they are extremely rare, but once you find them, they stay there for a while. Yeah, normal supernovae are, the facilities that we have right now are really not well matched. It's kind of sad. We would need a Chandra thing dedicated to supernovae.
Thanks. Okay. I will ask another question. So
Yeah.
And you use machine learning algorithms to detect your supernovas. And you told us that first you remove everything that is known not to be supernova, but also your machine learning algorithms will only detect what you taught them to see as a supernova. Do you have plans for the outliers that are
yeah, teaching machines to tell you when something doesn't fit? Yes, that's a huge there's actually a huge line of research right now that is going on in trying to understand what is the best way to actually find outliers, and yes, there are many different approaches that you can take, and I think that what we will see in the next few years is completely new way of how we go about identifying transients. And yeah, I do expect machine learning to become more and more prominent in our lives as astronomers. But yeah, I think that your question about, okay, how do you tell a machine not to put things in a box? That's a very interesting problem. Yeah.
Great to know. I didn't know that there were already fields dedicated to understand that.
Yeah.
Okay. We have time for a last question. Okay, I will ask. So my last question, if I'm given the time. So concerning the LS4 survey, that it's very interesting, and you told us also that 90% of the products of the data will be public. Yeah. When will it start, and how? What type of data will be available? Images, catalogs?
Yeah. So when okay. So we are, as you know, the biggest issue is for anybody else is all the delays associated to COVID. both in terms of getting access to the location in the mountain, but also in terms of having actually pieces of hardware delivered. It's been a little bit of a challenge. But I hear from Peter Nugent, the PI of the survey, that we are targeting December 2022 as a start of operations for LS4. And our goal is to actually integrate our triggers with all the LSST ones, so that people would not have to tune in into a different, like a different like broker or anything similar, but they would get the same types of alert. Then definitely we are committing to make public all of our findings in terms of news sources and as much information as we will be able to release. So we committed to ESO to give more than 90% of the data all public, and then the limit will be basically a limit of the bandwidth.
Okay.
But it's something very close to our hearts that the data should be public once for a philosophical standpoint. I strongly believe in sharing resources, but if you want to turn into a more practical point, especially in time domain astronomy, Swift clearly demonstrated that to get the best science, you need to have your data distributed as fast as you can to as many people as possible, because there is way too more data than a single person or a single group can handle. And discoveries are enabled by an effort by everybody. So it's convenient from a practical perspective, and that's something I particularly believe into from a philosophical standpoint.
Well, thank you very much. Sure, it will be a very interesting project and products coming out from this project. I think we have no raised hands, so I think there are no more questions. And if there are no more questions, we will now wrap this up. And as always, this webinar talk will be available on YouTube for access anytime. And thank you, everyone. And especially thanks for Dr. Raffaella Margutti for making yourself available so early in your local time, because we're in California. Thank you very much for giving this amazing talk.
Thank you for having me. It was a pleasure. Bye.
Everyone, have a great day. Stay safe, and I hope to see you all again on our next webinar. Thank you. Bye-bye.
Bye-bye, people.